Hello folks, we're back with more math. We've been dealing with line integrals and conservative fields so far. So we saw that calculating work and circulation when we have conservative fields was very easy because of the fundamental theorem of line integrals. But the question remains, what happens when the field is not conservative, like when you have something like friction, okay? So how would I calculate work integrals or circulation integrals? Or flux integrals for that matter, when the field f is not conservative. So that's where Green's theorem comes in. Green's theorem actually works on any field. We've already seen that when we have conservative fields, calculating these line integrals was very easy. So you would apply Green's theorem for fields that are usually not conservative. Okay, so that's when you would usually apply Green's theorem. Green's theorem is going to work for any field regardless, but that's when you'd want to do it. Before we start, we need to define a few things. I'd like to define the divergence and the circulation density before we start. So we're gonna be doing stuff in two dimensions right now for Green's theorem. Green's theorem is on the plane. So we're going to take a vector field, mi plus nj. Again, m and n are not constants. These are going to be functions of two variables. Now the divergence or the flux intensity of f at the point xy is, we're going to abbreviate it as div f, okay? That's dm dx plus dn dy. In other words, it's m sub x plus n sub y. Now what that measures is basically how much fluid is flowing away from the point xy. Okay, that's a measure of how much stuff is going away from xy. And the circulation density of f at the point xy is, we could say it's curl dot k. So it's another name for it is the k component of the curl dot k, and that's going to be dn dx minus dm dy. So you can abbreviate it as n sub x minus m sub y. Now what this would do is, if you have, I don't know, if you have some kind of velocity field of a fluid, let's say the fluid's kind of turning around like a whirlpool, okay? So you've seen all those movies where the ship kind of goes in, keeps turning. So that's it basically. So if you stuck a paddle into a whirlpool, into a velocity field, how fast would the paddle sticking directly in the z direction, how fast would it turn around itself? That's what the k component of the curl is. So what we're going to use Green's theorem to evaluate integrals. What Green's theorem does very successfully is it changes these line integrals around closed curves or loops. Okay, so when you're trying to do these line integrals around loops, it changes them into double integrals that we're already very familiar with. So I'm just going to state Green's theorem. I'm not going to prove it. Actually, for nice regions, the proof of it is not that bad. Green's theorem's proof is not bad. It's just that generalization of it is a little tedious. And I mean, most of you guys are going to be engineers anyways. So I'm just going to give you the formulas and just show you some examples. So the Green's theorem states that if C is a piecewise smooth loop, in other words, is a closed curve, enclosing a region R, okay, so maybe it's something like this, okay, and here is R, and in the plane, and if F is a vector field whose components have continuous first partials, okay, on R, basically on a region containing R, then we can write these integrals. Remember, the flux was how much stuff was leaving this area R, okay, this how much stuff was leaving the curve, okay, and the formula for it was f dot n ds, and we had simplified it down to m dy minus n dx, okay, over the closed curve. Now Green's theorem miraculously turns it into a double integral. It becomes m sub x plus n sub y, okay? So basically it just becomes, remember that was the div f, so that just becomes the divergence integral. It's just, you're just integrating the divergence basically, okay? Divergence of f. Okay, Also, the second form of it is if you're trying to calculate f dot ds, the circulation or the work will do also. If you think about this as a velocity field, it's going to be circulation. If you think about it as as um, uh, uh, force field, it's going to be work. So in that case, m dot dx plus n dot m dx plus n dy is going to be the double integral n sub x minus m sub y dA. Now I highly suggest you memorize both of these formulas. Okay. If worst comes to worst, you absolutely cannot memorize them, just memorize one of them, because I'm going to show you in a few minutes that these are actually equivalent. Now this relates circulation to the curl. Okay, this was the curl, the inside was the curl, so this is the curl integral, this is the divergence integral. And now it's not that much of a surprise, right? Because the outward flux, how much stuff is leaving, has to do something with how much stuff is going away from each point. And the circulation around the boundary, well, that's supposed to have something to do with how much stuff is circulating, how fast stuff is circulating around each point, so they should be related somehow. All right, the first thing I want to show you is to show you that actually these are exactly the same thing. You just have to memorize one of them. Let's have them all in one shot if we can. Right. Okay, so the two forms are actually the same. That's what I want to show. Let's take two force fields, two vector fields. F1 should be m sub I plus n sub j, and F2 is minus n sub I plus m sub j. Now, if we use the second form, this form, f dot ds is equal to m dx plus n dy, so this is the bit you want to memorize, okay? Is equal to the double integral n sub x minus m sub y dA, okay? Then the second form gives us, for the first field, f1, m dx plus n dy is equal to n sub x minus m sub y dA. Now, if we apply 2 to f2, okay, now its m is actually minus n, so instead of n, I would put minus n, and its n is actually m, so instead of n, I would put m dy, and I do the same thing. So now I have to do m dy minus n dx, sorry, and then that's going to be equal to my plus mx dA. So m sub y plus m sub x dA. So that's going to be the first equation as we saw it. Okay. So the whole idea is just switching them around in the formula. Okay. So here, because the one with the dx, okay, became m sub y, and it became a minus, you would get a minus, okay, for this guy, and that's going to give you plus m sub m dy. Oh, sorry, my bad. I'm just rearranging terms. Sorry, my bad. I just rearranged the terms, so it became m sub dy, n sub dx. Here's what happens. Okay, so the one with the dx, okay, dx is gonna go to m sub y, so minus n is gonna be minus, that's gonna be plus, and this guy is gonna be m sub x. Okay, great. So I was just rearranging terms here. Sorry about that. Now let's see some examples. Again, you would want to use Green's theorem when your field is not conservative. That's when you'd like to do it. So I picked a field that's not conservative. We're going to do the component test to check it's not conservative. Let f be x minus yi plus x sub j. And let's take as our curve just the unit circle, cosine ti plus sine tj, when t is between 0 and 2 pi. Now, what we're going to do is we're going to verify both forms of Green's theorem, okay? Again, once you actually verify one, the other one is for free, but we're going to verify it anyhow to show that it works. First of all, this is not going to be conservative because the y derivative of this, of m, should be equal to the x derivative of n, okay? But m sub y is equal to minus 1, and n sub x is equal to 1. So minus 1 obviously does not equal to 1, which means f is not conservative. So it would not be easy to do these work integrals, these circulation integrals and flux integrals for this. Okay. Well, it's actually pretty simple because the curve is very simple and the function is very simple. But I mean, it would take you some time, which it's going to take us some time, as we're going to see in a minute. So this would be a great example to apply Green's theorem. Okay, so let's move this and have these two guys side by side. Okay, so what I did here was I just rewrote the field on top so that we can have it in front of us. So the first form of Green's theorem states the integral, the line integral over the curve of m dy minus n dx is the same thing as the integral over the region of m sub x plus m sub y dA. Okay, so just plugging this in, our m was x minus y di plus x dx. Okay, is equal to, now m sub x would be just 1, okay, and n sub y would be just 0 because n is x, okay, so 1 plus 0 dA. Now you don't even have to do anything here because we know the region enclosed is the unit circle, so we're just trying to find the area of the unit circle here, right, which is pi. You don't have to do anything, okay. You don't have to do anything. If you wanted to do it, remember, if you really wanted to do it, you want to get remember your stuff, you would want to write it as a double integral, right? And you would want to have y go from minus 1 minus x squared in the square root to y goes to 1 minus x squared, and this goes, x goes from minus 1 to x goes to 1. Okay, that's how you would want to do it. Dy dx, if you really wanted to feel like you want to do a trigonometric substitution problem or something like that, that's how you do it. But it's just dA, and the region is a circle, so I mean, yeah, you don't need to do any calculations. Now, okay, so this is great. This is great. This calculated the outward flux for us. Now, if you wanted to do it the old way, okay, our curve C was R of t equals cosine t I plus sine tj. Okay, so now I'm going to use, for x, I need to use cosine t, and for y, I need to use sine t. So dx is going to be equal to the derivative of this minus sine dt, and dy is going to be equal to, right, that's just dy dt would be cosine t, so dy would be equal to cosine t dt. So again, if we look at the integral m dy minus n dx over this loop, we have x minus y dy plus x dx. That's what I get from the field. And plugging in x, well, x is, as we said, cosine t, so x minus y becomes cosine t minus sine t. And remember, dy was just cosine t dt, so that's going to be cosine. I pull the dt's out at the very end. And n was equal to x, so that's going to be minus cosine t. dx is minus sine t, the whole thing in dt, so that's the integral we have. Now, once you make the simplification, you get cosine squared from multiplying these two guys out, a minus sine t cosine t, and a plus sine t cosine t. The two minuses make it a plus. So they will cancel each other out, and we have 0 to 2 pi cosine squared t. So for cosine squared, remember, we write 1 over 1/2 1 plus cosine t dt. So we're going to have 1/2 t, and this would be sine 2t over 2. 0 to 2 pi. This guy is going to be 0, so you get 2 pi over 2, which is again pi. So it gave the same answer both ways. Now, I mean, let's just be honest. This is just like two lines, and this is, oh my goodness, it's going and going and going and going. Even on a simple curve like a circle, I mean, just imagine how hard life would be if we had a horribly nasty curve, right? Horribly nasty closed curve, a bad loop. So I mean, Green's theorem makes things a lot easier if you can just memorize the formula. That's what I'm trying to say. Okay, now let's go back and now let's try to calculate the circulation integral, the curl integral. So the circulation would be this guy, m dx plus n dy, and Green's theorem's second form says this is supposed to be equal to n sub x minus m sub y dA over the region. Our region is again a circle, the unit circle. So plugging everything in, again, I wrote f here, copied f here. F was x minus yi plus xj. So you get x minus y dx plus x dy. Well, let's do the n sub x. Okay, so n is this guy. N sub x is just going to be 1 minus m sub y. M sub y is going to be minus 1. Minus a minus 1 would make a 2. Again, we have the integral of 2 dA, so that's just twice the area of the unit circle, which is just 2 pi. Okay, again, very, very easy to calculate. Okay, now if we do it the old way, for calculating the circulation, we already calculated in the previous page dx is equal to minus sine t dt and dy is equal to cosine t dt. So the integral x minus y dx plus x dy would just be cosine t minus sine t times, well, dx was minus sine t, okay, plus x cosine t, and dy was cosine t dt. So multiplying these guys, you get minus sine t cosine t, and you get the sine squared from here, you get the plus cosine squared from here. Now again, remember sine squared plus cosine squared equal to 1. So all we get is 1 minus sine t cosine t, this guy plus 1. Let me just write it here. Okay, so it's just going to be, I pulled the 1 in front, 1 minus sine t cosine t. Well, integral of 1 is t. Integral of sine t cosine t is sine squared over 2. Remember, this is just a simple substitution. Cosine t is the derivative of sine t, so if this is u du, kind of, u squared over 2. Put it back, you get sine squared t over 2. Again, evaluate from 0 to 2 pi. The contribution of this term is 0, so you just get 2 pi. And again, you get the same answer both ways. Now, again, I would much prefer doing the Green's theorem rather than doing it the long way around. Now, let's just drop the act of circulations and flux. Let's just say we're interested in a curve integral, in an integral around a curve. So we're going to do, on a closed curve, the line integral x squared y dy minus y squared dx. Okay, now, okay, so this time I picked a square. The corner is at the origin, okay, and it's bounded by the positive xy axis, and the lines equal to x equal to 1, y equal to 1. Now, normally you would have to calculate the line integral. You would have to break this up into two pieces. The first piece here, the second piece going up, the third piece like this, the fourth piece like this. Okay, you would have to break it up into 4 pieces. Why did I evaluate counterclockwise? Remember, in my previous lectures, I said unless mentioned otherwise, we're always going to assume our line integrals, our closed curves, are counterclockwise oriented. So this guy is counterclockwise oriented, and we want to do this integral. Okay, so we've dropped the act of flux, we've dropped the act of circulation. We're just interested in this integral. Now, what we're going to do is I rewrote the integral here. Okay, I rewrote the integral here. So we have the integral x squared y minus y squared dx dy dx. So this is this I'm going to say is equal to my m, and this I'm going to say is equal to my n. Okay, now then the Green's theorem stated that this would be m sub x, derivative of with respect to x, plus n sub y, derivative of n with respect to y, over dA. Okay, so let's do this. M sub x would be 2xy minus n sub y, plus n sub y, that would be just 2y, okay? Dx dy. Well, what is r? Because we're on the square, right? So remember, r squared goes like this. Okay, so this was 1, this was 1. So y is going to go from 0 to 1. X is going to go from 0 to 1, and y is going to go from 0 to 1. So it's going to be 0 to 1, 0 to 1, 2xy, 2y, dx, dy. It's a rectangle. It doesn't matter. If you want, you can write dy, dx. It's the same thing. So integrate with respect to x. You're going to get x squared y, 2x squared over 2. That's an x squared y, plus 2yx. Evaluate from x equals 0 to 1. So you're going to get y and 2y from here. So that's going to make a 3y. And that's evaluated from 0 to 1 dy. So that's going to be 3y squared over 2. And that's going to give you 3/2 as the answer to your integral. So it's a very nifty trick. It's a very nice trick. The Green's theorem is very, very nice. It converts these in line integrals around closed curves to double integrals that we're very familiar with. So it's a very nice trick, especially when the fields that you're interested in, when these components that you're interested in are not conservative, okay? Especially when they are not conservative. Like this one is not conservative, right? Because m sub y would be just x squared and n sub x would be 0. So it's not a conservative. It wouldn't be easy. We wouldn't be able to do the fundamental theorem of line integrals. All right, folks, that's it for today. I hope to see you later on. Take care. Bye-bye.